It's a great pleasure to introduce Amita, who is today's speaker. So she's in fact she has IIT Kanpur connection. She's a MSc from and PhD from IIT Kanpur, and she is very well known in the community of plasma physics. So her research interests are nonlinear and turbulent plasma, laser plasma interactions, strong coupled plasmas. She has DAE SRC Outstanding Research Award. She's a fellow of all the 3 academies of India, and she's a GGC Bose Fellow, and she's the editor of Physics Letters A. Okay, so today she will talk about laser plasma and magnetic field generation. Okay, Amita, it's all yours.
Thank you, Mahendra, for inviting me to deliver a talk in your seminar series. So I'll talk about mechanism of magnetic field generation in electron beam plasma system, where I'll show that the boundaries play a crucial role. So this is the outline of my talk. So I'll impress upon the importance of energetic electron beam transport in plasmas. And they're important in various contexts, especially in the inertial confinement fusion scheme, particle acceleration, etc. And typically the beam, when the electron beam propagates inside a plasma, since plasma has already has a combination of electrons and ions, so the background electrons get moving and they provide a return shielding current. And this combination of forward and return currents are fraught with certain instabilities, which lead to the generation of magnetic field, which can often turn turbulent, and then it affects the beam transport. So these instabilities are electromagnetic in nature, and they are the conventional instabilities are well known. But in today's talk, I'll talk about a new mechanism of B field generation, which we have observed in our simulations, and which there's proof in the experimental studies also about this particular new mechanism. So I'll talk about that in detail. So why is electron beam transport in plasma of importance? Electrons are a very good source of energy. You can accelerate them very easily. And unlike lasers, they can propagate inside even in overdense regions of plasma. What do I mean by overdense? Because if you look at the laser frequency, then inside the plasma, it satisfies this kind of dispersion relation, where omega square is omega p square plus k square c square. And omega p square depends on the plasma density. So if the laser frequency is higher than the plasma frequency, only then k can be real and the laser can propagate. So overdense plasmas, you cannot use lasers to heat the plasma or do something. So there, the choice is that electrons, energetic electrons need to be used. Because often it is desirable that you want to pack a certain energy in electrons and make them propagate along a desired path and stop at the desired location in plasma. That is very important in the context of especially the fusion context. So let me briefly talk about it. There's a relevant example of fast ignition. It's a variant of inertial confinement fusion scheme, where in the ICF scheme, you compress the target so that using lasers, and the objective is that you also create an ignition spark. You make the compressed target hot at a certain location from where the burn wave can start, where it can fuse and the burn wave can start. So in the fast ignition scheme, one adopts 2 laser pulses. First is the slow nanosecond laser pulse, which is utilized for compression. And then a fast sub-picosecond laser pulse is sent for igniting the target. Now, why are these 2 pulses used? that you can understand from a comparison between conventional ICF and fast ignition scheme. In the conventional ICF, one is sending laser pulses from all the direction and one compresses the target. And the compression itself creates a hot core. One expects that this compression creates an ignition at the center, and then fusion will occur and the burn wave will keep propagating, and this is how the fusion reaction will occur. But there are problems associated with it because you need a very precise spherical symmetry of the target as well as the laser pressure, which is difficult to achieve. And then there is a mixing of hot and cold fluid, and you require more laser power to basically heat the entire target at around 10 kV fusion temperatures. So this becomes quite inefficient. So people devised another scheme in which you compress the target and let it be cold. So the compression is easier. You require less energy, less pressure to compress it. You can tailor the compression pulse in that fashion. And then after the target is compressed, you send a fast igniter laser pulse. Now remember, the target has already got compressed to supersolid densities. So now the laser observes a overdense target. So it cannot penetrate inside. What it does, it generates energetic electrons at the critical density surface. What do I mean by critical density surface? It is the plasma density where the laser frequency matches with the plasma frequency. So there, the laser stops and gives its energy to electrons, and these energetic electrons then move deeper into the target, and the hope is that they will deposit certain energy and heat the ions, and then the burn wave can go on. So basically, the propagation of electron beam inside the plasma is very crucial in this context.
Okay, just a question. What is the density now, the super compressed plasma density in?
It's actually quite high. It is 10 to the power 26 grams per cc. No, 10 to the power 26, sorry, not grams. 10 to the power 26 number per cc, something like that.
I see.
Supersonic. More than that.
I see. And omega p is equal to omega at the surface.
Yes, it is.
So
for laser, it is. I think 10 to the power 21 or 22 numbers per particles per cc is the where there is a matching.
I see. Okay.
So you can understand this from this schematic. You compress the target, and so it has a plasma corona. So target is something like this, and where it's not to scale. So you have a high density compressed core, and there is a tail. So the igniter pulse stops here and generates energetic electrons, and you want the energetic electrons to stop inside the core, because if they're too energetic, you want high energy also, but it may happen that the energetic particle electrons, the Coulomb collisional cross section of electrons with ions, it's inversely proportional to the cubic power velocity. So that reduces. So it is desirable to have, in fact, turbulence here. So it's one of the schemes where you desire to have turbulent magnetic fields so that there is an anomalous stopping of electrons within the target. And there are evidences that it does indeed happen. So this is a good side of turbulence, so to say. So now the question is that, if you had vacuum, then the energetic electrons with currents higher than the alpha limit will not propagate, because you will have the self-generated magnetic field will turn the trajectory of the electron current. But interestingly, in plasma, there is the beam propagation can happen because plasma provides for return shielding current, and the return currents basically neutralize the forward beam current, and so there's a complete neutralization and there's no magnetic field, so the current can plow through the plasma medium. So this is what happens inside the plasma. Now, but this combination of forward and return currents, they are unstable to several instabilities, and one of the well-known instabilities is the Weibull instability. Basically, it tells you that the light currents attract each other. So this is the direction of propagation of current, and you can see that B field ultimately starts getting generated. But the point to note is that at initial times, the transverse structures in B field are very small. They are typically, if you look at it, they are typically, if you look at these structure sizes, they are of the order of electron skin depth. What is electron skin depth? It's a C by omega P. But with time, the nonlinear effects, there's an inverse cascade, and then these structures, you can see they coalesce and become bigger and bigger. So you get bigger structures only at a later stage. And there were some simulations which were carried out by Sentuku a long time ago, I think in early 2000. And with the periodic box, he showed that how when the currents are sent, there is a separation leading to Weibull instability, and there's a current sheet formation ultimately. These sheets then tear and coalesce and form these current channels, which ultimately gets turbulent. And in fact, even after they form channels, when basically the forward and return current get separated, then the Kelvin-Helmholtz instability would set in, as we showed in some of our fluid simulations subsequently, and we could show that there is a lot of turbulence generated. Magnetic turbulence that gets generated. So what are this? Are there any experimental signatures of this turbulence? That was the question. And there were a series of experiments which were performed by Professor G. Ravindra Kumar group at TIFR. And what he did is that he has a target, and then he sends a pump laser pulse which ionizes the target, and it also, in the same plasma, it is overdense plasma, it generates energetic electrons which go inside. There's a forward and return current and so on, which the effect of which is measured by a probe pulse, which is timed, and you can keep sending the probe pulse after various delays, and from the polarimetry data, one can infer about the magnetic fields.
So that Amita, to get, so forward current and return current basically cancel. That's why magnetic field you're not expecting at the first approximation. Is that correct?
Yes, correct.
But the nonlinear effects are basically
no, even linear. For the equilibrium is forward and return currents, let's say. So there's no forces, nothing is there. But then the perturbation will grow because light currents attract each other.
I see. Okay. But they are not like currents. They're going in the opposite direction.
They are going opposite. Forward is going. There is a certain, there would be a plasma is inductive. So it provides for the return shielding current.
Okay. All right. Great. Continue, please.
Yeah. So, in fact, this was the preliminary. We had started in early 2000 to work on this, and we were able to show this is the magnetic field data, experimental, and this is our fit using this 0D modeling. And we were able to show that the fit is agrees very well with the experiment. And on that basis, this was the source term for the creation of magnetic field, and this term corresponds to the dissipation. So from the estimate of tau, which fits this curve, we were able to estimate the resistivity in the medium, and it turns out that the value of the resistivity turns out to be anomalously large. It was of order of magnitude larger than what typical value would have been. So that was an evidence of anomalous resistivity, and that may arise only if you have a turbulence playing a role. Subsequently, the TIFR group was able to also generate not only, this was only time evolution, so an integrated over space. So they also generated polarograms from the CCD camera or something, and they were able to measure the magnetic field at each pixel and provide a spatial pattern for the magnetic field. And note that this was the transverse direction. So this spatial pattern was in transverse direction as a function of time they are measuring. So that is what you see, that the magnetic field is appears to be random, and it grows and then it damps a bit. And if you see the power spectra, they're very regular. It had a slope of -2, and this, in fact, we didn't have data to accurately say that it is -2, but it was closer to -2, which corresponds to typically the EMHD turbulence spectrum. And then later on, they did experiments for longer duration, and they saw the spectra to evolve. So there's a definite region of kink that appears at these at later values, and these have been averaged over thousands of laser shots and many runs over the years. And we were able to identify that this kink appears when the ions at later times, when the ions also get involved in the dynamics. So here, there was only EMHD effects, but later on, the ions, the time at which this kink appears and the location at which it appears, they testify that the ion involvement dynamics, and that was studied and pointed out by us, and this was published in 2017. And so this was the background, but there's something else to be noted. If you look at the power spectrum, then the power spectra peaks at longer scales, and they're much longer than the electron skin depth. And right from the very beginning, very sub-picosecond, and even the earlier times, Ravi and his group has been able to measure, they are always peaking at the longer scales, at scales which are much longer compared to electron skin depth. But if you look at the conventional Weibull instability, which is often used to explain this, the growth rate maximizes at electron skin depth, and it's only subsequently, and which is at quite later time, that you would get inverse cascade related effects to have a spectral contribution at long scales. So this is the puzzle. So why is it happening? As you can see, these are some snapshots I have showed that the transverse scale length is very fine. It is, it goes towards nonlinear cascade is also very slow. It doesn't go to scale lengths which are, these scale lengths, if you look, they are of the size of laser spot size or bigger. So this obviously cannot explain the experimental fact, and you can we compared it also. These are the experimental signature. The peak is, the highest value of the spectrum is at longest scales. Whereas if we consider these simulations and look at their spectra, they peak at around the skin depth. And there's a decay in the power at long scales. So this is the puzzle. So there's a clear deviation from conventional understanding, and we need to understand this. So it was in this context that we started looking at this problem. We wanted to address this particular puzzles, and so let's look at the obvious differences between experiments and simulations. Simulations, all this along, they were at only periodic boundary condition, which implies that the cross section of the beam is typically infinite, was considered to be infinite. And there was a complete current balance was assumed initially. The beam was non-divergence, homogeneous density, and so on and so forth. Whereas experimentally, the laser spot size is finite, and it decides the transverse extent of the beam. There could be finite currents because this balance, I mean, plasma has, after all, certain inductive time. So this will not be instantaneous. So there will be a certain imbalance in current. The beam could be divergent. The plasma density could be inhomogeneous. So after all, which of these differences are crucial? So that was our question. And we carried out simulations. Let's say this was case A, where we chose the beam width to be finite. And then, so this was the beam width. And there is a background plasma here. We also tried with the vacuum region. And you can see that nothing changes. I mean, even here, the scales appear at very, the skin depth size and subival, which takes over and so on. So this doesn't work. And then, so these are some snapshots which I have kept in case the movies doesn't show up. And then we considered another case where we chose a certain imbalance in the initial current. So like we introduced a current perturbation initially. So in this case, there's a drastic difference you will observe. Immediately, the transverse scale of magnetic field is quite large. There's an emission outside of the radiation, and there is the magnetic field scale length survives at a long scale, which is also shown by the spectra. And it's only later that this oblique viable structures appear, and even the cage instability at the edges are observed in some of this. This was drastically different, and very different if you choose a finite current perturbation initially. So these are some of the snapshots. As you can see, that it is only later that the viable has appeared in this, and something like cage also starts forming at a very later time. And if we look at the spectra, then for case A, as expected, the spectra peaks at the skin depth, whereas for the case B simulations, where we had a finite extent of the beam, as well as a finite imbalance in the current, the peak is very, the spectra is higher at longer scales. It was very clear. And
so what is the slope here?
Yeah.
Slope. What is the slope for these cases? Left figure slope.
Same.
What's slope? The power law for the left figure.
The same. It is same as
-2.
Same as the experiment is. It's early time. I mean, like the ions have not come in. Yes. And then we also evolved the magnetic field energy in the system. And for the case B, you can see that there is something happens at the initial time, which is makes a rapid increase in magnetic field energy. And then typically here, both the cases have similar, but it saturates also at a higher value. This is a log scale. So how do we understand it? Actually, the streaming flows have a lot of free energy source, and unstable excitations are usually negative energy modes. And in fact, what was happening in the case where we chose a finite current imbalance, the currents were oscillating and acting like an antenna. The power is gone. So, and that antenna radiated waves. And because of the loss of energy from radiation, the radiation was providing the dissipation in the system. So we also carried out a theoretical analysis to illustrate a novel possibility, to have a finite boundary effects taken into account. And so let me go through that theoretical analysis. And so this is the simple model that we chose, that we have 3 regions, and in the center there is a region where there is a balance between forward and return currents, and here in 1 and 3 region there's only background plasma. So the equilibrium current is 0, the density is matched with the ion density, so there's no force here. And for if we do the linearized instability analysis, then these are the 3 fields which are crucial, because it's a 2D variation. So only B, Z, XY is the plane, so only B along the Z axis becomes important, and E1X along electric field along the flow direction and the perpendicular direction. So these are the 3 fields. And if we linearize the equation, we get something like, so these are from the momentum, relativistic momentum equation for the electron equation of motion. And these are the linearized Maxwell's equation. This is the current term. So one gets basically 10 variables and 10 equations, and you can simplify it to get this, like one can eliminate all the fields in terms of E1X, and one gets this as the final equation. So one more. This as the main equation, where F2 and G2 are these. S1, S2, S3, S4 are all the variables indicating the equilibrium parameters. And you can see that S1, S3, S4 will be positive. Sorry, S1, S2, S4 will be positive. S3, depending on this, can be negative, but S3 square appears. So this is also positive. And if we are looking for purely growing modes, then we substitute this. And if you integrate this equation over a finite region, minus A to A, where this that the beam was finite, we get something like this term. So there's a boundary term appearing here. This boundary for periodic simulation would be 0. And then this would be this would be equal to 0, and that can happen by the balance of these 2 integrations. So, but in the presence of boundary terms, in fact, this can be shown to be basically the Poynting flux of electromagnetic radiation. So if this term is there, then you have to balance, both these 2 terms can balance with this particular term. So this E1x prime, which is prime means y derivative, this need not have to be very high. So you don't need short scale structures to balance this particular term. And so with the help of this, one can have structures which are long scale, and this contribution from here can be smaller. And this indeed happens. You can see, and in fact, these are the comparison of the 2 terms. And you can see that the boundary term is 0 for case A, where I had chosen current to be negligible. And the second term grows, but it grows very slowly, the time scale of viable instability. You can see this scale is 10 to the power minus 5. Whereas if you have case B, then both of these terms are important. And this scale is also one order higher compared to this. So both these terms then can balance the effect, and they occur at, and so they're 10 times higher compared to this case, and they can balance the other term very nicely. So there were some concerns which we have published a paper on this. It is in PRR, but there were some concerns which the referees had. Actually, 3dim we did in that paper also. So I mean, like, some concerns up till now would be that what is the relevance of the third dimension? We have chosen sharp profiles. The beam duration is finite. Time typically in experiments. So we have now started working on that. This 3dim case also, it happens. This was shown, as you can see, that this appears. This particular mode can be seen. You see first it appears. This long scale structures appear. And so only later that this viable and at the edges, the Kelvin-Helmholtz mode appear. So this is observed even in 3 dimension. And this is a better picture of that. As you can see, the B field as it first, this is the long scale that appears. This is the beam propagation direction, and this is the transverse scale. But here you have negative magnetic fields, here it is positive. So this is the beam width is the relevant scale. And then as it propagates outward, the Bible appears at the center, there's a KH instability, and this is the electron density part. Bible instability is very clear in this plots, you can see. And this is the zoomed in plot of that. Sorry, this is the Kelvin-Helmholtz instability here. And here you can see the Bible oblique modes which are appearing, which are characteristic of the Bible mode. 3D also, some snapshots which show this particular things. This was all there in the PRR paper, but we started looking now at, the we had carried out simulation for certain sharp profile, but what happens when the profile of the beam is not that sharp, but it has smooth. So we chose different beam widths also, and we also chose the different the tangent hyperbolic fall. That epsilon characterizing the fall was chosen to have different values. And we also added in some simulations, the vacuum region. In all these cases, the spectra peaked at long scales as expected. We observed this kind of new feature. So it was not dependent on the sharpness of the profile as the referee was concerned about. We also chose a finite beam in the temporal direction. So propagation direction of the beam is finite. Then even at the leading edge, you get these long scale magnetic field structures. And if the spectra again shows the long scale behavior. This is Y versus T plot for the magnetic field. And in the vacuum region, if you see these slopes, they correspond exactly to the light wave. So it's indeed the radiation that has been emitted out from both the boundaries that is making a difference. And in the plasma, you can see some places the slope is steeper compared to that of C, and that is because plasma has the phase velocity of the plasma for electromagnetic wave could be higher. And there are certain these slopes which are which are not that, slower compared to C, and these basically are different modes which are observed in the plasma, which we are analyzing. So this, in fact, confirms that it is a radiation which is going out, and it has a dispersion relation of the electromagnetic. Omega is equal to Kc. So the characteristic of the emitted radiation, as I mentioned, in vacuum region, the slope matches the speed of light, and the plasma medium, it's a steeper slope indicating higher phase speed, and the observed frequency typically is plasma frequency and higher harmonics, as well as some such modes. So what are the observations? We in fact saw 3 distinct phases of evolution. The first was that we observed long transverse scale of B field generation. And it typically happens with a lot of radiation coming out from the edge. And only then, after that, you observe Weibull and Kelvin-Helmholtz. Like Kelvin-Helmholtz occur at the edge, and Weibull occurs in the bulk of the beam region. And it explains the experimentally observed spectra at long transverse scales in the magnetic field. And as I said earlier, radiative losses here, these are, for the beam system where there is a lot of energy in the beam, it tries to go to a minimum energy state and any kind of dissipative coupling. In fact, it was known that if you have a collisional damping, then the growth rate of Weibull instability increases. So here, by choosing a finite current, one has added an antenna, and that has resulted for radiative losses, which is acting as a dissipative coupling to the system and leading to a very fast as well as long scale magnetic field generation. So finally, I'd like to say that this provides for the understanding of faster mechanism of long scale magnetic field generation in plasmas. And the system wants to relax to lower energy state, as I had already mentioned. So the dissipative coupling through radiative processes helps, and and it helps the instability to grow faster. One can see the analogy of this happening in the plasma with the fundamental modes of the star, whose instabilities are driven by dissipative effects, or something like if it excites gravitational radiation, then even the star, these rotating stars are found to emit gravitational radiation, and they lead to an instability mechanism, which was studied by Chandrasekhar, Friedman, Schutz, etc. And we feel that this is an electromagnetic equivalent in some sense to that particular what was happening in gravitational wave radiation in the star is, it's a electromagnetic equivalent, something like that. And in fact, this would also have a lot of relevance to astrophysics, because there you have encountered jets coming out, and often such areas can be threatened. Like you can have a lot of plasma medium, which can provide for counter-streaming currents, and this kind of radiative losses can be present there. So this is where I would end my talk, and this was a collaboration, and along, as you have seen in my talk, this was a series of years of collaboration with the experimental group of TIFR. And in this particular paper associated with the finite beam effect, we had these people, and we had published one paper in PRR. Now some new people have joined from IIT, and we may have we are in the process of preparing a new manuscript in this particular area. So thank you very much. I'll be happy to, if there are any questions, I'll be happy to address them.
Okay, thank you, Amita, for a very nice talk.